Okay, so we're going to start this chapter 9. In chapter 9, we're talking about confidence intervals. And in particular, today, we're going to look at confidence intervals for a population proportion. So this is my categorical data. I need to refocus this here. So remember, we just started last week pulling this categorical data and everything we're doing. So just to reiterate what I just said, in chapter 8, we used information about a population to describe a sample like X bar and P hat. That's so unrealistic. That's not really what happens. So what really happens is what we call inferential statistics. So where we take our sample and we see what's going on with the population. So here in chapter 9 for confidence intervals, what we will do is we'll use a sample to estimate and describe our population values of mu or p. So the population mean or the population proportion. So we need to go over a few things before we can get right into confidence intervals and what they look like, how they're made, how we're going to do this, all of that. So the first thing is, let's talk about a point estimate. Point estimate, this is the value of a statistic. Remember, statistic just means from the sample that estimates the value of a parameter. Now, we don't really talk about parameter, but this is my value from a population. So what I also want to add here is when we talk about a point estimate, we talk about the best estimate. And today, our point estimate, our best estimate will be p hat. Remember, p hats are sample proportion. I'm going to write this off to the side. And how we calculate p hat is x divided by n. I'm going to write all of this over here to the side. So we're going to remind ourselves that p hat is our sample proportion. Remember, it's that percentage, right? Part out of the whole, people of successes or people that answered yes to a question. We just introduced this later last week, right? So it was like, I believe, Wednesday last week. How I calculate p hat, and we didn't have to do this last week. We calculate p hat by taking x divided by n. So x is the number of people that said yes to our question, or we can say it's the number of individuals. I don't like to say people because we're not always studying people, right? It's a number of individuals that have what we call a specified characteristic. That's X. So it's the number of people that answered yes to our question. Then N is just my sample size. And that's what makes up my p hat, my sample proportion. My sample proportion is what we call our best estimate or our point estimate for our population proportion confidence intervals, which we'll see that in just a minute. So let's talk about confidence intervals, what they are, what we're really doing, and then we will look at the formula and how that formula breaks apart and what we're using. So confidence intervals, I never really write this out. I will a few times for you guys, but I want you to know I always abbreviate using CI. I even just say CI. So if you were in my Stat 2 class right now, we talk about CIs all the time, and I just say CI. I hardly ever say confidence interval. I guess I'm being lazy. So CIs or confidence intervals, what are they? And how should we think about these? So these are intervals. It's an interval of numbers, but it's an interval built around our point estimate. And today, like we just discussed, that point estimate is our p hat value. So it's built around it. That means p hat is the center of my interval. We use intervals because p hat varies from sample to sample, right? We talked about this last week. My p hat will vary, right? The proportion of individuals who said yes to the question is going to vary based on my sample, right? Sample to sample, it's going to change. So we cannot expect our sample to give us a perfect picture of the population. So I can't just say, oh, well, I'm going to use the one sample and say, oh, that's definitely what my population is. Well, it's not, because even if you just take one sample and you take a second sample, your proportion will change, right? So you can't just take a sample and say, oh, that's what's going on in my population. So we build an interval. We use an interval. So it's a grouping of numbers, right? An interval of numbers that will say, and we'll talk about our population proportion in that way. But it's based on our point estimate, our p hat value. And we have a level of confidence. So our level of confidence is the proportion of intervals that will contain the value p. If needed, or I'm sorry, if repeated, let me get this. Sorry, I don't like to have it too messy. So if repeated, samples are obtained. So what I'm saying is that we're going to have a confidence level. So we won't just be building one type of confidence interval all the time. We're going to have a certain level of confidence. And that level of confidence, it's going to tell us what proportion of intervals. So it's going to tell us what percentage of intervals that we build will contain our value p. If we get multiple and multiple and multiple samples and keep building different CIs over and over and over again, that kind of thing. Okay, that's what I'm looking at when we're talking about this level of confidence. So when we're talking about this level of confidence, a lot of times we talk about a 90%, we talk about a 95%, or we talk about 99%. These are the most common levels of confidence that we talk about. And what I want you to know is that with more confidence, and this is a tricky concept, I will have a wider interval. It's a tricky concept because most people think about confidence levels that they feel better about their calculation. They feel more confident in their calculation. That's not what confidence means in that respect. Okay. It doesn't mean that same thing. And this meaning is that I have more confidence, meaning I'm going to include more numbers in my interval. Therefore, my interval will be wider. And that means I'm more confident in my CI, including P. So if I have a 90% CI that I build, my interval would be smaller. So the range of numbers would be smaller compared to a 95 or compared to a 99. So as I increase my confidence, my interval becomes wider and I'm more confident because I include more numbers. My range of numbers is larger. That's my confidence level. What I want you to think is that your calculation for a confidence interval is always the same. Your calculation is not changing. So you're never going to feel more confident in the calculation. So it's not that. And you're never going to feel more confident with your sample. You're always hoping that your sample is a good sample, meaning there's no outliers and stuff like that, right? To throw it off. So you're always hoping that you have a good sample. So confidence level is just truly how wide your interval is. So the higher the number, the wider the interval. It's like a hard concept for people to understand that. They always think more confident that you feel better about your calculation, so you have a wider interval with a lower number. And that's not what it is. Okay. All right. So I want you to think about these confidence levels, and I don't want you to say it's the probability. It's not about a probability. So I want you to think about this, that if I build 100 confidence intervals at the 90% level, then that means 90 out of those 100 confidence intervals will include my value P, my population proportion. That's my unknown value. So 90 out of 100 would include P. If I did 95%, then that would mean if I built 100 intervals that are 95% level, 95 out of that 100 would include P. And again, with 99, it would be 99 out of 100. So it's this percentage will include my value P. Okay. I don't want you to think about it as a probability. So some people might say, oh, I have a 90% probability of P being inside my CI. It's not that. Because think about it, probability means likelihood, right? Likelihood of an event occurring. The reason why I don't want to talk about it in that way is because P is a set value. We just don't know it. It's just unknown. So P is the population proportion. So maybe it's the proportion of US students, college students who prefer chocolate ice cream over vanilla. It's a set number. I just don't know what it is, right? Because I haven't done any work. And I can estimate that value by taking a sample, but I won't know for sure what that number is. But it's not a likelihood because that number is a set number. I just never know actually what it is in the end, unless I survey every single college student in the US. Does that make sense? So we don't want to talk about it as a likelihood or a probability. It's kind of like a little fine line there. So some notation that we're used to seeing a little bit. If n times p times 1 minus p is greater than or equal to 10. Now I'm going to continue with the statement. It's an if-then statement, but I need to address something. We don't know p, right? I just got done saying it's an unknown number. I will never know this number. So I actually use p hat, what I do know. My best estimate for p is p hat. So I use my sample proportion in my check here. Then we estimate. That p hat follows a normal probability model with a center at p hat and a spread at the square root of p hat times 1 minus p hat over n. So right here, I have my center, my spread, okay, my normal model. There it is. So what I'm saying is if my normality check comes out, n times p hat times 1 minus p hat is greater than or equal to 10, that means it's symmetric, right? This means I have a normal shaped data set, bell-shaped. Then that means I can use my normal probability model to calculate probabilities or percentages or anything that I want to look at, right? Percentiles. So I need to show that's true before I can calculate probabilities or percentiles, right? Because I don't want to use a normal model unless I should be using a normal model, meaning it's normal, okay? So that's one of our, what we call a requirement or a condition or an assumption. My requirement is that it follows my normal model, okay? We're used to that. We've saw that notation last week, right? Actually, the last 2 weeks, I believe. So let's take a look at our formula for a confidence interval. So I gave you all this information about what these confidence intervals are, what they're doing a little bit, and let's take a look at the formula. So the formula for my confidence interval, it's always going to be the same formula, and you'll see even next class, it's the same formula. It's just what I plug in changes. So my formula for a confidence interval is always point estimate plus or minus margin of error. Now it just changes what makes up these values. So here, my formula for a CI to estimate P, okay, I'm going to add that right here because that's what we're doing. We're going to estimate our population proportion, P. Then we use P hat for our point estimate, plus or minus our margin of error, which is made up from two numbers, which is our Z at alpha divided by 2. And I'll need to go over that because there's a lot to say about that, times my standard error. And that's my spread right here. The square root of P hat times 1 minus P hat over N. So take a look up here in my notation. P hat is the center of my curve. P hat is the center. Look at my formula, plus or minus. That means I'm going to have P hat plus my margin of error. That's going to be the top or my upper bound for my CI, right? Then I have P hat minus my margin of error. That will give me my lower bound. So think about it. P hat is the middle. It's the center. It's always right in the middle. Okay. Let's talk about what these are. So the Z at alpha divided by 2, people get a little overwhelmed by this. This just tells me the number of standard errors away from the center. So it just tells me how far I am from the center. And my center here is P hat. This depends on my confidence level. So this is where that confidence level comes into play. So if you're 90% confident, 99, 95, whatever it is, could be something random like 92, doesn't have to be one of the 3 most common. And that's going to tell me how far I am from the center. How many standard errors? Z, remember that standardizes. So let's talk about this alpha divided by 2 right here, this little chunk right here. You're not multiplying, you're not dividing anything. This is a location only. It's just a location. It's just telling me where I am, okay? So it's just a location, and what it means, it's the area in each tail of my curve. So alpha is the total area. Oops, I put an A, but it's a total area. Okay, I'm going to show you some pictures here in a minute. And then of course, this right here, like I already mentioned, this right here is standard error of p hat. Okay, we've already talked about that last class, my standard error. Right? So let's talk about this z at alpha divided by 2. I feel like there's a lot to talk about with this, and I want to make sure everyone's on the same page and we all feel pretty good about this. Now, if you, I can't remember where it was, but if you, it was not last week, the week before, team assignment, it was like the last part, you would have done this already. If you didn't get to it, it's okay. You're not going to be behind or anything. It was just to kind of give you guys a little taste of what we're going to be doing. So let's just take a look at the most common Z values or most common confidence levels. Okay, so we'll just take a look at these most common CI levels. So we're going to look at the 90, 95, 99. So I'm going to look at this curve. Here's my normal curve, sort of. It's not great. Now, if I'm looking at a 90% CI, so I'm going to write 90% up here. What that means is the area in the middle is 90% or 0.90. My Z values are these numbers right here and right here. So all it is telling me how far on my standard normal curve, my Z curve, how far am I from the center? This is the center. How far am I? And it's the same distance between these two. Okay. So when I talked about alpha divided by 2, that's this area in the tail. So this right here is alpha divided by 2, which in this case is going to be 10% divided by 2, which is 5% or 0.05. Does that make sense? It's 10% because I'm looking at 90%. 100 minus 90 gives me 10%. Divided by 2, I have 5% in each tail. See that? 0.05 in both tails because it's centered, always centered. Okay. Now, the team assignment asked you to come up with these values, and I kind of helped you do this because you could do it with your calculator. I'm going to give you these. You can memorize them. You can write them down so you can refer to them, but it's nice to know how to find these values, right? So I'm just finding either this value or this value because I want you to know one is the positive to the right and the other one is the negative. They're both the same number. It's always like that because you're looking at a Z standard normal, so you bring your center down to 0. Okay. So what I'm looking at is what is this number when the area in the tail to the left is 5%, 0.05. Okay. Or I can say, what is this value here when the area to the left of this value is 90 plus 5, so 95%. You see that? So here, my standard errors away, which is my Z at alpha divided by 2, is going to be plus or minus 1.645. I'm just writing it big there so we see it, but I'm going to write it here, 1.645 and 1.645. So you guys might see that this looks a little familiar from a couple weeks ago. That's my 90. So let's take a look at the other two. So we're going to look at the 95 and the 99, okay? So my 95 here, and this just says 0.95 is in the middle. Okay. So if 95% is in the middle, then that means the area in my tails between both of them, alpha, is 5%, right? 100 minus 95 is 5. I'm going to divide it by 2. So that means the area here is 0.025 And the area over here is 0.0. But what I'm really interested in is this value here or this value here, and it doesn't matter which one. I'm going to show you why in a minute. But this one's the negative and this is the positive. So my standard error here is going to be plus or minus 1.96. Okay. So you can easily find this with your calculator, right? You can do the inverse norm, put in 0.025, you're going to get negative 1.96 out. 0 and 1 as your centering spread, right? Because it's a standard normal. And then over here for 99.99 is in the middle. So then I have 1%. So that means I have 0.5%, right? Left over here. So that's 0.005 and 0.005 here, okay? That area. Again, I'm looking for this and looking for this. Just one or the other. Doesn't matter if you have the positive or negative. So my standard errors here is going to be positive or negative 2.576. So I'm going to make a note. Use the inverse norm function. So I don't care if you use it on Minitab or your calculator, and you can find it to find these. Z at alpha divided by 2. You see how alpha divided by 2 is just a location? Just how far away you are. Just how wide am I here? That's what we're looking at. Okay. All right, let's take a look at an example so we can kind of put all of this together and make a little bit more sense of what's going on. So see how up here I wrote to estimate P? That's exactly what we're doing. So anytime we're looking at a confidence interval, you're going to see the word estimate. So if you see the word estimate, it means confidence interval. It means we're doing this. Okay. So let's take a look at this example here. So for this example, I have in a random sample of 150 RIT students, 93 support a pass-fail grade option. We want to estimate, right? There's the word. With 95% confidence, the population proportion of all RIT students who support the pass-fail grade option. Okay. So let me just underline a few things and to give you, so I'm having trouble with my paper here. So we know what we're looking at. How do we know this is a CI? How do we know what we're going to do here? Okay. So when we're looking at this, it talks about a sample, right? It starts talking about the sample of 150. This right here is my N, right? It's my sample size. And it says, okay, 93 support. So 93 have said, yes, they support the pass-fail grade option. That's my X. And right here it says, estimate with 95% confidence, right there. As soon as I see this word estimate, I know it's a CI right away. I don't even have to think about it anymore. So I know I'm looking at a CI here. And what we're going to do is we're going to estimate P right? That's my population proportion right here, population proportion. Or even if it just said proportion of all, that would mean population proportion. I'm going to estimate P with 95% confidence level. So I know my 95% confidence level is going to take me to this, right? What I'm using for how many standard errors away, my location. We're going to draw this out because it's so helpful to kind of view everything at once. So we need different things. So I'm going to rewrite my formula. So it's always going to be the P hat plus or minus my Z at alpha divided by 2. And I don't ever fill that in, but you can because it's your location. You know what it is if you know 95% here, right? Alpha divided by 2 would be 2.5%, right? And then my standard error. So I'm just going to fill it in with a formula. So that's the square root of P hat times 1 minus P hat over N. Then I'm going to start filling things in and solving for wherever I can, right? So I'm gonna use this area over here to the right to kind of solve for some of these values, and I'll plug the numbers in. So first of all, it says P hat, right? So I need to actually get that value. Remember, that's X divided by N. So my P hat is going to be 93 out of 150. Now, when we were talking about probability, it was great. I just left it as a fraction. But now when we're in here, I'm actually going to do something with it. I'm going to add and subtract. So I don't want to leave it as a fraction because that just makes life too difficult. I'm going to divide it out and get it into a decimal. So I'm going to write this and use it as 0.62. So that's my P hat. So I'm going to use that right here, 0.62. That's my best estimate, my point estimate for my population proportion P, 62%, right? But it's just, it changes for every sample. So I'm not going to say, well, it's 62%. I don't know. I'm going to build an interval. So I have my Z at alpha divided by 2. Remember what we said about Z, and Z depends on my confidence level only. So my confidence level is 95%. So my Z value is either negative 1.96 or positive 1.96. And it doesn't matter which one you use. And the reason why it doesn't matter is because you're adding and subtracting. So it doesn't matter. I always just use the positive, but it does not matter. 1.96. It's always that for 95. It's always 1.96. So that's what I'm saying, you can just memorize them. Excuse me. Now my standard error. So my standard error of P hat is equal to the square root of P hat times 1 minus P hat over N. So I want to fill that in and find out what number this is. So remember, this is the spread in my standard error. So I'm going to use a 0.62 in here, and then 1 minus 0.62. And then N was 150. So I'm going to multiply those and then divide and then take my square root. So when I do that, I find that this standard error is 0.0396. That's my spread, 0.0396. So I'm all set to find my confidence interval. So what I'm going to do is I'm going to multiply these two, and then I will add and subtract. So I'm going to multiply these. I get 0.077616. I'm going to add it. So my upper bound is equal to 0.62 plus 0.077616. And that leaves me with 0.6977. And then my lower bound is equal to 0.62 minus 0.0776. Okay. So then when I subtract these, I get 0.5423. That's my lower bound. It's like a lot on one page. It looks messy. I'm not even done with my page. So how we write this answer is in an interval form. So 0.5423 up to 0.6977. We need to know what this means, right? So I'm going to write a statistical, what we call a statistical interpretation. So the interpretation is very important, more important than the calculation, I would say. So I'm going to show you how to have your technology do this for you, but it can't do the interpretation. So I'm going to give you a blanket statement and feel free to use this, or you can write your own. So we are, and then you're going to use whatever percent, whatever level, confidence level you are. And I'll write it out on another page. Whatever confidence level, confident that the population proportion, now you want to say of what? So it's the population proportion of, and then who are we studying? So that's the RIT students. And what is it that we're studying? Those people that who support, right? So who support the pass-fail grade option. I guess I just started doing two things at once. Is between, I'll show you what I mean by that. My lower bound, so 0.5423, and my upper bound. Oh my Lord, I just started writing upper bound because that's what I said. And 0.6977, okay, value. So what I really wanted to, I was really going to write a blanket statement, and I'll have to write it on the next page because I started intertwining both. So I'm 95% confident. So I want to let you know what do I look for when I'm grading something like this? I look for what confidence level you have. I look for the word population proportion, and I look for your objects in the study. So it's who you're studying and what you're talking about, so that they support that pass-fail grade option. And then I actually look for your answer of your interval. So the blanket statement, I'm gonna move this, but I'm not gonna take it away completely. I'm just gonna move it a little bit out of the way. So our blanket statement is, we say we are, whatever my level is, confident that the population proportion, and then you're going to say of, and then you have your context and variable is between your lower and upper bound. Okay. So this is your confidence level. This is going to be your lower bound and your upper bound. And then this is context of the problem. So make sure you include the variable, meaning what we're studying. So this is the who and the what we're studying. So this is like your blanket statement for your interpretation. This was the particular one for the problem. I was trying to do the blanket and then I was going to do the particular, but I just started talking about the problem itself. Okay. So we are that. So what does this mean, right? So this is a statistical conclusion, which is fine, but what does it mean if you're actually just going to talk to someone, right? Maybe you want to talk to your roommate and say, oh, I did this study. So what it means is that between 54% and almost 70%, right? 69.77, so like 70%. So between 54 and 70% of RIT students support that pass-fail grade option. That's what we're saying. Okay, so you could actually just report that to someone that's not in stats class. This is our statistical conclusion. But if you were just going to just draw a conclusion without being statistical about it, you would just say between 54 and 70% of RIT students support that pass-fail grade option. Okay. I want you to know there's like some follow-up questions we could talk about. I only have like a minute. No, I get 3 minutes. There's some follow-up questions, right? So a follow-up question could be, does the CI show that less than 72% of students support that pass-fail grade option? That could be a question, like a follow-up question. And what you're looking for is the entire CI to be true for that statement. So it said less than 72%, right? So if you have a less than, then that means the entire CI must be less than. I'm going to write that down. So these follow-up questions or statements if you have a less than statement, what you're looking for is for it to be true when the entire CI is less than. So it's whatever your number is. So that for this example, yes, every number in the CI is less than 72%. So yes, that's a true statement, okay? If similar for the more than statement. So a more than statement is true when the entire CI is more than. So whatever we're talking about. So for example, if we're going back to this example here, you could say, is it true that more than 50% of the RIT students support that pass-fail grade option? Well, yes, because my entire CI is greater than. So yeah, that is true. Okay. It would not be true if you said 55. If you said 55 is more than 55% of the students say that it's true, that's not true because you have a number that goes below 55, right? 54. I don't care if it's right close to the edge. If it's closer to this edge, it doesn't matter. If that number is inside my CI, that's not true. The only time it's true if you have it in the CI is if you're talking about an equal to statement. So an equal statement is true when the value of interest, whatever we're talking about, is in the CI. Okay. So for this one, I could say, oh, 60% of the students say that they support that pass-fail grade option. That's true. 60% is in my CI. I could say that all the way up to 69.7 and all the way down to 54.2, right? I don't want to, or 3, I should say. I don't want to go outside of that for that to be true. So that's an equal statement. So I have different statements, a less than, more than, and equal to statements. Those are like my follow-up statements, guys. So just keep in mind, these CIs, they estimate our population values. And that was for categorical data proportions. In next class, we're going to discuss this for numerical data with means.